In this lesson, we're going to be looking at limestone, its uses and chemical properties, including environmental issues. In the use of limestone, it causes problems to the environment. We're going to be looking at how that is. We will learn about thermal decomposition. We will also look at alkali and alkaline properties of solutions. In one of the chemical reactions, limestone is turned into an alkaline solution. But for now, alkaline solutions are substances with pH ranging from 8 to 14. But limestone can be turned into something called calcium hydroxide, which is an alkaline solution, which will have not a high pH, but it will be around about 10. So it's like a mild alkaline solution. So we're going to be looking at how that is used. This alkaline solution is used in neutralizing acid soil. So that term is something that we're going to need for this lesson. Acid rain, you must have heard about this. Acid rain has a pH lower than 8 and it in the range of 6 or 5. So acid rain has got a pH of 6 or 5, and that causes the acidity, and that can damage the limestone. So we're going to be looking at how acid rain damages limestone. Neutralization, as I've already mentioned, calcium hydroxide, which can be made from limestone, can actually neutralize acid soil. So we're going to be looking at how that is very useful. Limestone can also be used to make cement, mortar and concrete in a particular way. So we're going to be looking at those things in detail. What you see here is a type of limestone rock that is found in nature. And what you see here is a small bit of that rock, but it is slightly different type of rock. That's why it's got slightly different colors. But what we should know is all limestones mainly contain a chemical substance called calcium carbonate. So we can pretty much assume that the chemical formula for limestone is calcium carbonate. Limestone is obtained by quarrying process, which means it's dug up from the surface of the earth using elaborate process of building roads and trucks going in and out, and using huge digging machines, including use of explosives to break the limestone rock. It's mainly obtained in huge blocks of limestone, which can be used as it is. See, limestone blocks like this can be used straight to make buildings, and there are many buildings, historical buildings, made straight with limestone, and they are very stable. However, there are lots of other uses of limestone. When it is turned into something else, such as cement, you got many other uses. Let's have a look at some of them. What you see here is one use of limestone. Limestone is crushed into powder, mixed with clay, and heated very strongly. You get cement. Cement is a very useful substance in making buildings. As you know, bricks are all stuck together with cement and water paste mixed together, and it is really rock solid, and it is it gives very stable structure to the buildings. So cement is such an important substance that's made from limestone. When cement is mixed with sand and water, it becomes a substance called mortar, which is here mortar, and the mortar is used to stick bricks together in making buildings. Very useful substance. Here's another useful substance made from cement. When cement is mixed with sand and aggregate, you get concrete. Aggregate is bits of rocks of about this size. So this concrete is very hard and extremely strong, and this is used to make lots of structures such as bridges. As you can see, big giant structures such as these are only possible because of concrete's extreme strength. And here is how it is made: huge concrete slabs by just cement, by mixing cement, sand, aggregate with water. Concrete is made, sometimes reinforced with steel to even further strengthen it, but putting steel in gives additional flexibility to the concrete in addition to its strength. It also gives that little bit of flexibility which prevents it from cracking. So here are the uses of limestone, a summary of what we have seen so far. What you can see is limestone when heated strongly with clay powder. So limestone powder plus clay powder heated strongly to give cement, but cement can be mixed with sand to give you mortar. This is used to build the walls by sticking the bricks together. Cement, sand and aggregate, which is the small rocky bits mixed together with water, that gives you concrete. When it's dry, it's a very solid and strong substance, and that's used to make giant structures such as bridges. So far we have seen some uses of limestone, which is making cement and mortar and concrete. However, there is another very useful substance, calcium oxide, also made from limestone here, but we have not yet come to that, as we need to understand the chemical reactions of limestone first, and then we'll come to understand how calcium oxide can neutralize acidic soil. But we need to remember that is another use for limestone. We are now going to look at chemical reactions of limestone. One of the most important chemical reactions of limestone is this thermal decomposition, where thermal stands for heat energy, and decomposition is breakdown in chemistry. And don't confuse this with the decomposition in biology. Biology, decomposition means rotting organic matter. So any dead or rotting matter, we refer to that as decomposition, which is bacteria and other fungus feeding on dead material. That's a different thing. In chemistry, it's breakdown of a substance into two or more new substances. So that's thermal decomposition. How does that work? All you have to do is calcium carbonate, you take it in a test tube or tongs and you hit it strongly, it breaks down into two substances. So calcium carbonate, you heat strongly and you get calcium oxide plus carbon dioxide, and this reaction is very important industrially, as it produces this calcium oxide, a very useful substance, as we can see in a few minutes. So this carbon dioxide gas is produced as one of the product, and this is a simple laboratory setup to actually test and show that it is indeed carbon dioxide that is being produced. The gas that's produced is passed through lime water and it's bubbled through, and you get a white cloudy precipitate like what you see here. So this is the start of the test where gas is being bubbled through, the carbon dioxide is steadily bubbled through lime water. As you can see, lime water is really clear, just like water, and slowly it gets cloudier and cloudier, and it becomes real white cloudy precipitate where you can't see through anymore. So you get like a solid powder dispersed in the tube, and that is the test, which is a positive test for carbon dioxide. Now you can say for sure that this gas that you pass through the test tube is indeed carbon dioxide. Okay, so that's thermal decomposition reaction, a very important industrial reaction which produces this substance calcium oxide, which has got many uses, as you've just seen. This is used in neutralizing acidic soil in farming. Another thing worth pointing out is that this substance here, the white precipitate that you get here, is calcium carbonate. So we started by decomposing calcium carbonate over here, and then you get it back by bubbling it through lime water. Let's see how that works. Calcium carbonate, you just seen this reaction. This is thermal decomposition, calcium oxide plus carbon dioxide. This carbon dioxide, you pass it through calcium hydroxide, which is lime water, and this is aqueous, which means it's a clear liquid, and this is a gas. What you get is calcium carbonate solid, and this is the white precipitate that you see here. and of course water. So you get calcium carbonate solid, which is where we started from. Calcium carbonate gives this gas. That gas passed through calcium hydroxide gives you back calcium carbonate, which you see as white precipitate here. Let's have a look at a series of reactions involving heat, starting with heating calcium carbonate, which is limestone. And what's shown here is a classical setup of a series of reactions. Over here you're heating the limestone, which is calcium carbonate, on a tripod strongly with a Bunsen burner, and what you will be left behind here on the tripod is calcium oxide. So calcium carbonate has decomposed, carbon dioxide is left. Okay, and when you take the calcium oxide and add some water to this solid calcium oxide, what you have here is calcium hydroxide. Okay, and this is still a solid. It's a slurry like paste, and which is left here. Now if you add excess of water, some of the calcium hydroxide will dissolve in water and produce the lime water, what we refer to as lime water, which is here. So this is after adding excess of water. You get calcium hydroxide, CaOH2, but this time it is aqueous, which means it's become a solution now, dissolved in water. And you filter this. What you have here is the clear lime water, which is again the same substance as this, but given a name lime water. Okay, so we call this as lime water, but this is essentially calcium hydroxide, a clear solution of calcium hydroxide. Now, when this calcium hydroxide aqueous solution, which we call as lime water, if you pass carbon dioxide through, like what you see here, over here you're passing carbon dioxide, you're blowing through this, passing carbon dioxide. What happens is this calcium hydroxide reacts with this carbon dioxide, forming calcium carbonate again. So what you have is here you get the cloudy precipitate forming in the flask. So what was clear here, a clear liquid here, becomes a cloudy liquid here, and the cloud is a white solid powder. As we know, it is back to calcium carbonate. So this solid powder that we get here, which is the precipitate, is calcium carbonate now. So we are back to where we started. Okay, so let me go through this again. First you heat the calcium carbonate here, and that becomes calcium oxide. So calcium carbonate heated here becomes calcium oxide. When you add small amount of water, it becomes a slurry like paste, which is still a solid, and it is calcium hydroxide solid. You add more water, some of the calcium hydroxide dissolves in water, and it becomes calcium hydroxide aqueous now. You filter it, the clear calcium hydroxide gathers here, where the solid calcium hydroxide is left behind on the filter paper. We call this clear calcium hydroxide as lime water. I must add this 2 here. So this is lime water, what we have here. And then if you pass carbon dioxide, you just have to blow through this or pass any carbon dioxide from another chemical reaction. You bubble it through the lime water. What you end up is the white precipitate, the white solid, this calcium hydroxide reacting with carbon dioxide, giving you calcium carbonate. Okay, so we're going to see this cycle of reactions without all this experimental setup now. Okay, as you can see, you first have the thermal decomposition reaction. To the calcium oxide you add water to get calcium hydroxide. This is now solid. You add more water, so more H2O, and then filter. What you get is a clear solution of calcium hydroxide this time, and we say AQ, meaning it's aqueous, and it is now dissolved in water. Okay, so this is our lime water, and this just looks just like water. It's clear. Now if you add or pass carbon dioxide through this, carbon dioxide gas through the lime water, what you end up is you're back to the calcium carbonate solid, which is the white cloudy precipitate that you get from this chemical reaction. So whenever you pass carbon dioxide through this, you're back to calcium carbonate, and this is referred to as limestone cycle. Okay, so once again, you get calcium oxide from calcium by heating calcium carbonate to calcium oxide. Add water, you get calcium hydroxide solid. Excess water filter, you get clear calcium hydroxide. Solution, which is lime water, you pass carbon dioxide through it, you get the calcium carbonate white cloudy precipitate. It's worth remembering this substance here is an alkaline substance. We'll come back to this as it is a very useful substance in neutralizing acidic soil. Alkaline solution, and you can get this by just sprinkling solid calcium hydroxide or solid powder of calcium oxide in the fields where crops are grown, before crops are even grown just in the soil where it's acidic, and it will neutralize the acidic soil as it will produce this alkaline substance. So here's a summary of the uses we have seen so far. Limestone powder heated strongly with clay powder gets cement. Cement mixed with sand gives you mortar, which is very useful. Cement mixed with sand and aggregate gives you concrete. So these are all building material. You also have something very useful for farming, which is calcium oxide. This actually neutralizes acidic soil, as this substance is neutralizes acidic soil. Why does it neutralize this acidic soil? Because this substance or this dissolves in rainwater or any other water to produce an alkaline solution. Okay, and that neutralizes the acidity in the soil. What we also need to know is, do other carbonates show similar reactions? For example, thermal decomposition reaction. Now, you already know calcium carbonate decomposes when you strongly heat it to form calcium oxide and carbon dioxide. Would it work for magnesium carbonate? Yes, it does. Magnesium carbonate do decompose into magnesium oxide and carbon dioxide. So it does work for magnesium carbonate. Copper carbonate. Copper is a transition metal in the middle of the periodic table. But this is in group 2. So this calcium is a group 2 metal, magnesium is a group 2 metal. This is a transition metal, copper carbonate. It does work in the same way. As you can see, there is a pattern here. They all produce their oxides and the carbon dioxide gas when they thermally decompose. But if you look at group 1 carbonates, for example, this lithium carbonate, yes, it does give the same kind of reaction, but the formula is slightly different. As you know, carbonate has got 2 charge and lithium has got 1, so it's got this slightly different formula, Li2CO3, but it does do the same thing, lithium oxide and carbon dioxide. But not all group 1 carbonates decompose at the temperature that you can reach with the Bunsen burner. Now, Bunsen burner can only go up to 1000 degrees, around about 1000 degrees, but these carbonates require even higher temperature. So that's something that you should be aware of. Not all group 1 carbonates. So this is a group 1 carbonate, that's a group 1 carbonate. Not all of them decompose in the same way. So you can't expect to decompose or break down sodium carbonate and potassium carbonate by just heating in the same way as you did for the other carbonates. What you see here is another reaction, another chemical reaction of limestone, calcium carbonate reacting with acid. As you can see here in this tube, you have chalk, which is limestone powder. Calcium carbonate powder reacts much faster, and this is a piece of limestone. Because it's got higher surface area, it reacts much faster. This is reacting slightly slower, but you can still see lots of bubbles are produced, which means it's a gas being produced. It's a new substance made, and it's a chemical reaction. So slowly this limestone will dissolve. As you can see, why limestone statues get dissolved and attacked by acid rain. So this gas is one of the products. There is another product which you cannot observe, is a salt, calcium chloride, which is dissolved in that liquid there. So that's the product you cannot see. What you can see is that carbon dioxide. But as you know already, how you can confirm that it is indeed calcium carbonate is you pass this gas that's coming off from this reaction through lime water, and if the lime water goes cloudy, then we know it is carbon dioxide, and that's a way to confirm that this gas produced is carbon dioxide. Let's have a look at the reactions and general patterns now. Yeah, what you see here is the same reaction in a word format: calcium carbonate, hydrochloric acid. We use in laboratories dilute hydrochloric acid, and that's enough to perform this reaction and to observe it. Hydrochloric acid, calcium carbonate, which is as you know, limestone, and this gives a salt, calcium chloride. Now this is dissolved, you cannot see it. Carbon dioxide is something that you can see as fizz being produced, a gas being produced. Water is also made, and that's a liquid that will be present after the reaction. The gas will go away. So what will happen is the mass of the calcium carbonate and the reactants together will keep on decreasing as this carbon dioxide escapes into the atmosphere. Here what you have is a symbol equation of the same thing. Calcium carbonate solid, which is limestone. Hydrochloric acid, dilute hydrochloric acid, produces this salt, which is a soluble salt. That's why you see this aqueous here. You also get carbon dioxide, which you see as a fizz, or in other words, it's called as effervescence. It's also another word that you can use instead of fizz. You see effervescence, and that is due to the carbon dioxide gas here. You also get water left behind. So there are three products that's made. Let's see, if you take a group 1 carbonate, such as sodium carbonate here, and react in the same way, you can see it produces similar products. A salt, calcium chloride here in the case of calcium carbonate. Here you got sodium chloride, as we are using sodium carbonate here. So you can see there is a pattern here. Carbon dioxide and water. All carbonates do produce carbon dioxide and water when they react with hydrochloric acid. What about magnesium carbonate, which is another group 2 carbonate? Would this produce the same reaction as these two? Yes, it does, in a very similar way. You get MgCl2, which is a salt, and you get carbon dioxide and water exactly the same way as these other two reactions here. Carbon dioxide, water, carbon dioxide. You can see a pattern here. All carbonates do react with acid, and it produces calcium, salt, and carbon dioxide and water. That's a pattern. You can of course confirm that this is carbon dioxide by passing through lime water and looking for that cloudy white precipitate. Now you should be able to understand why statues made of limestone get attacked by acid rain. As you've just seen, all limestone mainly contain is calcium carbonate, and they are attacked by acid rain to produce this soluble salt. Of course, carbon dioxide and water are made, but this is the main thing. This salt is soluble and it gets washed away. So you get the limestone slowly chemically eroded. Okay, let's have a look at what are the advantages and disadvantages of the mining industry as a whole. Now let's look at quarrying in particular. By building a quarry in a place, the locals are definitely affected, people who are living around the quarry. But there are still some benefits. as well as disadvantages, and one has to consider both before constructing a quarry. Such as you get the advantages, namely you get jobs for local people, which is always useful, more money for local people, and they don't have to travel further for jobs available locally. Useful things made, as you already seen. A lot of useful things can be made by quarrying limestone. You get cement, such as cement, and you can now even make buildings straight away with limestone blocks. There are disadvantages, however. You get this noise from explosions and heavy machinery constantly made day in and day out, and then you get a lot of dust generated, not only by the digging process and explosions, but by the traffic, increased traffic through the villages, and more noise generated as a result of the increased traffic, possibly through the local villages. And so noise and dust is a problem. Eyesore, and you're left with this gaping hole in the middle of a landscape, which is not nice to look at. So it causes eyesore in the long run. And all the living things that used to live in this area would have to migrate elsewhere. They have to go elsewhere, so you get the habitats destroyed. Is another environmental issue. Even one last issue is whenever you heat limestone, you are making a lot of carbon dioxide. Now, as you know, this causes another problem, global warming. Okay, and so before you construct, or government proposes to construct a quarry, or a company designs and wants to construct a quarry in a particular place, they would have to consider all of these factors, how it affects the local residents and so on, before constructing a quarry in a particular place.